back into vectors. The section in chapter 7 that just never seems to end. Just more and more good stuff every time. It was almost apropos that the music that led us into this video was from Alice Cooper, No More Mr. Nice Guy, because after you see a couple more examples of applications, you're probably not going to think I'm a very nice guy for making some of the assignment problems that I'm going to give you guys. But we're going to try to do a couple of examples here. Now, in the last video, we did one quick example where we had an airplane and we had wind, and we added the two vectors together to find out the resultant of what was happening to the airplane with the wind affecting it. In this case, we've got something similar. We've got a person swimming from one shore to another shore through a river or of some type, or some small lake, and we have probably some kind of a river, because we have a current that's affecting the swimmer, and we want to make sure that the swimmer is going to get to the point that is that part of the race. In this case, it says Joe enters a triathlon and must swim to a buoy offshore and then back again. A current of 0.5 miles per hour flows due west. The way I've got my diagram here, this is going to be north straight up here. So it says if Joe starts at the closest point, this is J, this is Joe right here, on the shoreline to point B, which is where the buoy is at, in what direction theta, that'd be this angle right over here in my diagram, should he swim in order to arrive at the buoy? Because if he swims straight for the buoy, the current is going to shift him to the west, and he's going to end up down here someplace. So he's got to kind of compensate for this current and swim a little bit to the east so that the current will even him back up, so that when he arrives on the shore, he's not down here, he's right at where the buoy is at. Now we're going to assume Joe's swimming speed is 2.5 miles per hour. We're going to try to round this to the nearest degree. Because of the way I've got this set up, we are going to use the components, but we also have to think about this as, instead of setting this up exactly like the last problem, we got some unknowns here, but we can find those unknowns by the way we've got this set up. Now, we don't know theta, that's important, we got to have theta here. But vector V, which is actually Joe swimming, here kind of outlined in pink, his magnitude is 2.5, because he can go 2.5 miles per hour, and we're going to multiply that times the cosine of theta, that'd be the x value times I, and plus 2.5 times the sine of theta times the vector J. So that's this guy right here, but the current is going straight west, so that's the one in blue here that's kind of outlined in blue. So in component form, straight west there, that'd be like 180 degrees, and we know that the cosine of 180 degrees is -1, and that the sine of 180 degrees is 0. So we're going to end up with the current, which is 0.5 times -1, I, and then 0, or 0.5 times 0, J, so that disappears, and that's why we only have this one piece, this one component here. And as you can see, because he's going straight across, which would be due north, he's not going to the right or to the left. The overall swim from here to here, if there was no current, we'd go straight across to get from this point to this point. We're going to have 90 degrees here, and that means that the cosine of 90 is 0. The sine of 90 is 1, but we don't know k because we don't know the magnitude it would take. So we're getting to that point. That would be his true speed, will be that magnitude. So we'll have to find k down here where we ask for the true speed. Now the resultant here, which is the one kind of in green, is equal to Joe plus the current, vector V plus vector C. So I've already got these marked off. I went ahead and substituted them in. And this is going to equal vector R, which is this. So I've got this is equal to this. Now, with that stated, I'm going to say that 2.5 theta, let's write it down here, 2.5 cosine theta I plus 2.5 sine theta j plus -0.5 I is equal, and I'm going to write it again here so it's all in one line, 0I, come on, plus k times vector j here. I keep saying i's and j's and I forget to say vectors, and sometimes I even forget the notation. But that's what I meant. Sorry about that if I'm causing any confusion here. So now what I'm going to do is I'm going to take this and set it equal to this, because these are the i's. So if I combine these, I would have 2.5 cosine theta plus negative 0.5, and this is I, equals 0, I, vector I, so that would equal 0. So I'm going to have a nice little trig equation here to solve, just as you thought you would never see another trig equation. Here comes one right away. Cosine of theta is equal to 0.2. So I can find theta. I have to do the inverse cosine of 0.2, and again, no calculator to be found, so I'm going to have to depend on some notes that I took before, and I get 78.46, and this would be degrees. Now that would be this angle this way. Now it's not drawn to scale, but it's in the ballpark a little bit. So to answer the question, or I lost my spot here. In what direction theta should he swim in order to arrive at the buoy? Joe should swim at an angle, and I think we want this to the nearest degree here, and so to the nearest degree at an angle of 78 degrees. There's part A. Part B says, what's Joe's true speed? Well, Joe's true speed, I'd be taking this and set it equal to this. So I would have 2.5 times the sine of theta is equal to k, but we know what theta is now. I can plug this right in here, and I get 2.5 times the sine of 78 let's see, I got to the nearest degree, so let's just go with 78 now. Yeah, we'll go with 78 degrees here. I don't like doing intermediate rounding like this to get k. I think the first time I did this, I used the angle that was a little bit more specific so I could get a better read on this. I've got to the nearest degree. Let's do this so that we're not so far up. Nearest tenth of a degree here. So we'll go with 78.5, and then I can plug this in and not feel so guilty. So I'm going to get k 78.46 degrees. Get my calculator busy again, and I'll find k to be 2.4498 approximately. So to the nearest tenth of a, this is in miles per hour, is it not? It is. In miles per hour, Joe's true speed is 2.4 miles per hour. So it slowed him down a little bit, because remember and I'm assuming in still water he can go 2.5 miles per hour. It slowed him down a little bit because he was working against the current as he went a little bit to the right, 78.5 degrees from the positive direction to the horizontal. All right. Now the last two examples, it involved adding two vectors, but you can have more than two forces acting upon an object. You can have, as many as you want. So in this next example, to show you an example of what we're going to do here, we're going to use three forces acting upon a particular object, and I've got it kind of displayed here in this diagram here on the right. And so what I'm going to do here is I'm going to be adding all three vectors and to get my resultant R. So it says forces F sub 1, F sub 2, and F sub 3, all those are vectors, act on an object in the directions depicted in the diagram here. The magnitude of F1 is 32 pounds, the magnitude of vector F2 is 24 pounds, and the magnitude of vector F3 is 15 pounds. You're to write the resultant force, vector R, in terms of I and J. Now vector R is going to equal vector F sub 1 plus vector F sub 2 plus vector F sub 3. This would be a real pain to do it geometrically, but I think we can get away with it a little bit more by doing it in terms of components. and we're going to try to get our final answer in terms of I and j. So f sub 1 is equal to, now f sub 1 is right up here at 90 degrees. So what I'm going to do here is, and my magnitude is 32, so I'm going to write 32 the cosine of 90 degrees I plus 32 the sine of 90 degrees j, vector j. Now the cosine of 90 is 0, the sine of 90 is 1, so this turns out to be 32j. So that's simplified quite a bit because the cosine of 90 is 0. Now the next one is the one in pink here, that's f sub 2, vector f sub 2, and it has a magnitude of 24, and its angle would be 158, 90 and 68 more. So this is going to be 24, the cosine of 158, need a calculator, times vector I, plus 24, the sine of 158 degrees, times vector j. So I didn't bring a calculator, but I jotted some numbers down. Negative 22.25 times vector I. When you get done multiplying, that makes sense. Cosine should be negative in the second quadrant. And then plus 8.99j times vector j. All right, now I know I'm going to round my answer to the nearest tenth and such, but for right now, I'm just leaving the numbers as is. I don't want to round and then round again later on. So now I've got to find vector f sub 3. Its magnitude is 15, and its angle here would be all of this to here. So that's 320 degrees, so that's cosine of 320 degrees times vector I plus 15 sine of 320 degrees times vector j. And again, I've got this worked out. You should have a calculator close by, closer than what I have anyway. And I get 11.49i times vector I. And see, you're in the fourth quadrant, so this should be negative. And it is minus 9.64 times vector j. So vector r is going to equal the sum of all these. So I've got 32j plus, here, I'll just write it like this, minus, or negative 22.25i plus 8.99j plus 11.49i minus 9.64j. So I'm going to add up all the i's, so I just have these two. Should have a calculator with me. A little less than, or a little more than negative 11. What would that be? Negative 10. Let's kind of cheat here. Negative 10.76i. Negative 10.76 times vector I. And then I'm adding 32. This would be 40.99, 40.99. 31.99, 31.35, let's see, positive times vector j, and I hope that I have that worked out right. And I have 31 point, oh, I took it to the nearest tenth, so that's no big deal. And so now, to the nearest tenth of a pound, I'm going to go ahead and write this as negative 10.8i plus 31 point, looks like 4 times vector j here. And what do we want here? We want to write the resultant force in terms of I and j, so it's right here. So vector r equals negative 10.8i plus 31.4j. And this would be to the nearest tenth of a pound. Do I have everything written down? I have everything written down. Now all it asked for was the vector, so there's really not much of a sentence here. It's more of a statement. Usually with a story problem, we do want to write our answer out in sentence form. All right, now we have one more example to go involving equilibrium.